and that is interpolation and extrapolation. Okay? Interpolation and extrapolation. This is the last section of this unit that we're going to look at. But when we're doing linear regression, two things we have to pay attention to are what value is furthest to the left and what value is furthest to the right. Okay? Now notice we don't care what the y coordinate is for either of these. What we're looking at here is the x coordinate. Which one has the lowest x coordinate and which one has the highest x coordinate. And those are what are known as the poles in our data. The lower pole and upper pole. Now, you can see here, we have the scatter plot, we have the least squares regression line. All of our other data is between the poles. Okay? As you can see from this diagram, interpolation deals with things that are between your poles, or within your data, we could say. Specifically, interpolation predicts the values of the dependent variable using x values, or values of our independent variable, that are between the poles. Okay? So that's interpolation. Okay? Inter means between or within. Okay? So we're using x values that are within our data, within the poles, to determine something about our dependent variable, or to try to, really it's to try to predict a value for our dependent variable. Okay? Now, extrapolation, blow this up a little bit more. Extrapolation, you can see, is to the left and right of our poles. Here we're dealing with predicting values that use x values that are beyond the poles or outside the poles. Extra meaning beyond or outside of. Okay. We're using x values that are outside of the poles. This is where you have to really be careful. As we saw with the homework problem, okay, when we extrapolate this down to where x is 0 and we're giving away free gas, is saying we're going to have 489.4 customers an hour accurate? Probably not, okay? It's at least not very reliable because it's well beyond any of our other data, okay? And that's one point that we have to understand about extrapolation. The further you get outside of the poles, the less reliable our least squares regression line will be to approximate the value. Okay? So let's mention a few things here about interpolation and extrapolation. All right? First of all, obviously you have to find the least squares regression line. And that's going to be your model. And really you just evaluate that model for different values of x. Technically speaking, we should not plug in values for y and try to interpret what the x would be. Okay? Technically that's not an appropriate use of the model. Right? So we're only plugging in values of x and predicting what y, or what that dependent variable, would be. Okay? Another thing you need to do is identify assumptions you're making. Okay? One assumption that we're making is that our data follows a linear pattern, or at least an approximate linear pattern. Okay? So that's one assumption that we need to identify. Another thing is that if you are extrapolating, you are assuming that it is going to continue that pattern. All right? There isn't something beyond your data that's going to cause it to change somehow. All right? Again, looking at our gas station thing, one thing that we'd have to consider as we lowered the price is what's the capacity of the gas station? How many pumps are there? How many can it reasonably accommodate in an hour? Because that's going to put a cap. Also, okay. And another thing you would have to consider is as the station gets fuller and fuller, people are going to be less and less likely to go there just to save 2 cents a gallon or whatever. Okay. There are other factors that are going to come into the play of their decision when, you know, the price gets lower and the lot starts to fill up and people are realizing I'm going to have to sit there for 5-10 minutes until I can have a pump that I can fill my tank with. All right, so that's the kind of stuff when you're extrapolating, you're making the assumption that people don't care about wait time. Okay, and that the capacity of our gas station is unlimited. All right, if you were to extrapolate too far one way or the other. Okay. Another thing that you should do when you are extrapolating or interpolating data is to interpret the slope and the y-intercept. And you really do this when you get the least squares regression line anyways, okay, but especially here, identify what that slope is telling you. Identify what the y-intercept is telling you. Again, going back to this example, we said the y-intercept was if we were giving away free gas. That's how many customers we'd have. But also the slope. The slope tells us how many customers we would lose for every penny we increase the price. That's going to be an important value to identify, especially if we're using this for any kind of application or analysis. Okay, so interpret those. If you guys choose for your IA to do some kind of a correlation study, you need to do this kind of stuff. All right? If you recognize in your data that you do get a correlation, a great next step would then be to, not with your calculator, but manually find the line of best fit. It's not too hard. Okay, it would actually be an excellent addition to your IA. So you're interpreting that, or you're finding that, and then interpreting it, and then that's where the reflection aspect of your IA can come in. You can reflect a lot of that, and identifying assumptions and interpreting your data is going to be really important, okay? Which, by the way, we're going to be starting to look at the IA information next week, okay? Another thing, and this kind of goes with the assumptions, but identifying limitations of your predictions, okay? One thing to consider is the strength of your correlation along with the statistical significance of your correlation will determine how good a predictor your line of best fit is. Okay? If you have a weak correlation, the line of best fit is not going to be a real reliable predictor. Even if it is statistically significant, it may not be a great predictor of that dependent variable. Interpolation, we said, tends to be more accurate because it's within the data. Also, you can compare it to actual data values that are close and see if it's kind of close. extrapolation tends to be accurate as long as you're somewhat close to the poles. Okay? Now, there's no real hard and fast rule that I know of, at least, of how far away from the poles does it start to become unreliable. Part of that is dependent on how strong your correlation is. But that's just something to be aware of. Okay? One project I used to do with my algebra students when we were talking about linear equations, just for fun, and to kind of explain this limitations of extrapolation, is we would take 2 of the world record times for the men's 100-meter dash. Okay, supposedly the fastest man in the world is the man who wins the or holds the record for the 100-meter dash. Okay. So what we did is we took 2 years and times, and then we found the slope, and they would find the equation of the line. And then we would use that, and we would set y equal to 0, which would be the time. Okay? We would do the time as a function of the year. All right? Which we could do with correlation data. We just use more than 2. We'd use a whole bunch of the times and years. And while there is a negative correlation, is that going to be linear? Are people going to be breaking the record and it's going to follow a linear pattern? What's it going to be? What shape is it going to have? Yeah, it's going to be an exponential decay. So it's going down. It used to go down relatively quickly. Like if you look way back in the early 1900s, guys broke the record by like a full second or more. Now we're down to measuring it in thousandths of a second. You know, and guys are beating it just, you know, by minuscule times. So, number one, we were using an improper model, and I would talk to them about that. But also, we would then use that by setting y equal to 0. When will the time that it takes us to run 100 meters reach 0? To predict when teleportation would be invented. Okay? So, we had a little fun with it. But that's a case where we were improperly using extrapolation. Okay? We get unrealistic results. We were using a bad model to begin with. But still, it kind of has you get the idea there, how we have to be careful with extrapolation. Okay? So, what we're going to do is I want to just work through some of these. A little bit of this is kind of what we were doing yesterday, but we're going to take it further here, okay? For the first 3 parts here, I want you using your calculator, all right? If you don't have one, you're going to get one, all right? And use the data here. And then finish the, get these first 3 questions first of all, and then consider parts D and E. We have a situation here, we're looking at the amount of time a collection of families spends preparing homemade meals versus the amount of money they spend every week on fast food. Okay? So let's work through this and we'll discuss it once we have some numbers.
go to a stack. Mr. Hickson.
Yes.
So I found a weak positive correlation between gas prices in the previous problem and money spent on fast food in this problem.
It's a weak positive.
Yeah, it's not bad.
So the more gas costs, the more you end up spending on fast food.
Let's see what the R value is for that.
You don't need to sketch it for this, okay? Just get it on your calculator. All right, you should be able to get the scatter diagram on your calculator. If you go, I'm going to do that in here. So the least squares. That's what I just showed you. With 3.3, you were off the line. Yeah, it's not gonna. Yeah, you'll have to type in that second list again.
For R?
What you got for your A? Oh, okay, I did it right.
Oh, you
What did you use? Wow.
Yeah. Big negative for A.
Yep, for A?
Oh, it's M. Let's do it as an AX. I'll do it as an AX. Let's see if it's negative 12. Let's see if it's different.
Like it's very similar, just like a few decimal place, like one decimal higher.
I would guess maybe you type in a number on it.
I checked, I don't see it.
Huh, that's weird.
It's pretty much like I'll do it 0.87.
Yeah, no, I'm getting negative 8.61. I'm getting negative.
I must have missed it. Alright, so who else? Then it must be something.
Oh, I got what I did wrong.
It would be
85. That's it. But it just sort of data wrong.
You got different than Samantha did?
Yep, now it's 12. Got it. Negative 12.6.
Oh, wait.
You got negative 12.6.
Yeah, it's all in.
Me too.
Yeah, that's what it is.
For R?
Yeah. No, wait, no, yeah, R is negative 0.86.
867, right?
Yeah,
So that's
5.
like
That would be like a super, super negative. It's such a strong correlation. It is extended past perfect. It's like a Jesus correlation. This correlation is too strong. 12 times perfect. One for each disciple.
You got something slightly different.
There's a lot of things already. Reading an article about the Judas correlation. Hear about those?
Michael Harvey, Michael.
It's goats who are like, they go with the herd into the slaughterhouse, and all of them are slaughtered except the Judas goat, and they keep using the Judas goat because the Judas goat keeps the slaughterhouse fun. It's the so it leads the herd into freedom, and they all die except the Judas goat. They used Judas goats on the Galapagos Islands because they accidentally contaminated goats. So they were had to put them on farms they contaminated. Was to send in Judas goats. You know, seek out the other goats and they would feed it to other goats and then they would kill the other goats. Not that one. So it was like death follows me everywhere. It's great. Like it's the most sophisticated screw up farming practice because like everyone used to use it because it just works.
And say for 35 officers.
All right. Okay, so guys, what'd you get for? I'm not sure what's going on. Why yours is giving us a slightly different value. Yeah. Okay. There's got to be something in there. It's a little goofy.
Mine's 12.9.
Negative 12.9?
Nine.
I had 12.
Did you check your data for typos or for a missing decimal point or something? All right. Let me show you what I got here. Okay. R. It's a negative 0.8678. All right.
Yeah, negative 12.6.
Okay. Your least squares regression line, y equals, now it's, to go with IB rounding rules, we'll go to 2 decimal places, 12.65x plus 116.16. Okay? So we've got that. Real quick, what is the gradient going to tell us here? What's the slope or the gradient? Where gradient equals slope.
That's how much money you spend on fast food for each 12 hours you stop cooking homemade meals. So like for each 12.65 hours you're not cooking, you spend another $1 on fast food.
Is that right?
That's what it says.
That's actually backwards.
No,
Every hour, hang on, what's y? Y is money, right?
Yeah.
So,
every hour that you
listen, every hour you spend cooking is going to save you $12.65 that you would have spent on fast food, theoretically, okay? So yeah, it's minus $12.65 in money for every hour you spend cooking. The 116, what's that? Our y-intercept.
If you spend 0 hours cooking, that's how much you spend on fast food.
Yeah, if you didn't cook at all at home, that's about how much you'd spend on fast food. So, now, if you have 5 hours, where are you going to put that in here?
That's interpolating.
It is interpolating because it's within the range. We went from 2.5 to 9.1.
Plug it in for X.
Plug in 5. That'll give you approximately how much we spend, that family would spend on fast food. Okay?
You still have a test on Tuesday, Mr.
No, our test is on Thursday. Okay? Our test is on Thursday. Alright? We will be starting other stuff Tuesday, Wednesday. We're not going to review for 2 days. Alright? But our test will be on Thursday due to the holiday, Monday and Tuesday. Okay? Alright, have a great day.
What is the gradient?